Okay, so so far we have worked on in energy methods. We have worked on virtual work, um, unit load method. That if you have a complex system and if you want to obtain displacement solution at particular point in that complex system, then how do you use a unit load, replace it with the actual loads in the system, combine the information and solve for that unit load, right? So then in energy methods we also use principles which are based on potential energy, and there are many. Principle of stationary total potential energy, principle of uh, minimum total potential energy. So these are a couple of principles that we are going to study. They are basically very important when we try to use energy methods and identify systems characteristics. Okay, so let me write down what this principle says, and then we'll go through the details. So a conservative system is in equilibrium if and only if the virtual changes in the total potential energy vanish for all virtual displacements. So a conservative system is in equilibrium if and only if the virtual changes in the total potential energy vanish for all virtual displacements. We can also write this sentence in terms of an equation, and that would be a differential of the total potential energy with differential with respect to all the generalized coordinates virtual displacements. You sum them up over all the particles you have, or all the degrees of freedom generalized coordinates, and then you have this expression equal to 0. So virtual changes in the total potential energy vanish for all virtual displacements. So to simplify it, because now the virtual displacements, they are arbitrary, they can take any value. So we can say that the total potential energy differentiated with respective generalized coordinates is 0, where the generalized coordinates, the q, are q1, q2, so on to qn. Okay. So essentially what comes out of the principle of stationary total potential energy is that the variation of potential energy is 0 for equilibrium. Okay, so variation in the potential energy is equal to 0, and Um, Variation is just like differentiation. It Variation is just applied on functionals. Differentiation is applied on functions. So when you take a variation of a functional, you minimize or maximize that functional with respect to a function. In case of differentiation, you have a function and then you maximize or minimize that function with the help of a variable. So that's the only difference between a variation and a differentiation. So we can write the total variation of potential energy in terms of and then we can apply the Taylor series expansion of this variation. Then the second term would be times dqi or dqj variation. Yeah. And then you'll have, so the total variation is expanded using Taylor series expansion, where the first term is the first order differential of potential energy with respect to generalized coordinates times the variation in the generalized coordinates. Then the second term would be a second order differential, and then so on. But because these terms have lesser and lesser magnitudes, they are higher order terms, so we neglect anything which comes beyond the second term. Okay. So the principle of stationary potential energy, or principle of stationary total potential energy, gives us this expression. And then we already know that this term is 0, right, from the principle of stationary total potential energy. So we are left with this term. Okay. So this term is essentially a summation over the term which involves the second order differential of potential energy with the generalized coordinates. So the second order differential term times the variation in the generalized coordinates should be greater than 0 if we want our potential energy to be a minimum. So like in functions, when we have a function and we are trying to find maximum or minimum of a function, we differentiate it once, then we differentiate it again and check the sign of the second differential, right? If the second differential sign is positive, then our function is at a minimum. If our second differential sign is a negative, our function has a maximum. So similar characteristics go for variation as well. If we have a variation of a function, if the second order variation is positive like this, then our potential energy will be a minimum. If this term is less than 0, then the potential energy will be a maximum. So let's think about a case where we can visualize this. For example, if we have a surface and then we have The surface has this characteristic, and we have a small ball at this location, at this location, at this location. Okay. Are all these three states in equilibrium? If they are stationary, they all are in equilibrium. Means that if there is no perturbation whatsoever, then all three situations are in equilibrium. But what happens with the potential energy at this location, let's say? What happens if there is a perturbation? It will not be stationary. So this is what we called as unstable equilibrium. That a small perturbation in this state will result in a situation that this system is not in equilibrium. Okay. And here we have the potential energy which is maximum. So the system has the maximum potential energy at this location. As soon as you perturb, the potential energy gets converted into kinetic energy and you lose your equilibrium state. Okay, because an external applied load is always going to increase your potential, but the potential is already at maximum. So whatever you do, the energy is going to convert into kinetic energy. Now let's look at this situation. So this is an equilibrium. What is the situation with the potential energy? It is at its minimum, right? So it's a stable equilibrium. The potential energy is minimum. So what happens if you give it an external load? It goes back to its original place. The load temporarily increases its potential energy, but then it gets converted to kinetic energy, and then it always comes back to its equilibrium position. Okay. Then what happens here in this case? It's like a neutral case. So we call it still unstable equilibrium. It is still unstable because if you move this ball, it is not going to come back to its original position. So we still call it unstable equilibrium. But it's neutral. It's neutral in the sense that the displacement or the movement is not diverging. When you move it, it takes another equilibrium position. Okay, so it's a neutral or unstable equilibrium, which is neutral, and the potential energy. What can we say? We can say that the second differential here of the potential energy with respect to its generalized coordinates is equal to 0. Okay. So if the second order differential with respect to the generalized coordinates for the potential energy is 0, then you have a neutral equilibrium, which is this situation. Okay, this situation here. So with what we did, we can define principle of minimum total potential energy, which states that a conservative system is in stable equilibrium if and only if the total potential energy is a minimum with respect to the changes in generalized coordinates. So a conservative system is in stable equilibrium if and only if the total potential energy is a minimum with respect to the changes in the generalized coordinates. Okay, so we would have a stable equilibrium situation if potential energy is a minimum. Otherwise, we have an unstable equilibrium or a neutral situation. Okay, so we typically use energy principles to study stability. So there, when we design a component, we always look at maximum stress or yield stress, and based on our stress criteria, we define that the design should be changed or the design should be optimized. So let's say we have a material which is stainless steel. Just some recalling. We have the strain here, the stress here, and the stress strain curve looks something like this, right? Familiar with this stress strain curve for stainless steel or steel. Then we define this point as our yield point, this point as the maximum stress or strength, and then ultimate tensile strength, right? So this is our elastic range where the system starts to go plastic. Now, we generally design a component, take the stress strain curves for that material, find out where are the yield stresses or the maximum stresses, and define a failure criteria, right? And then we judge whether the design that we have is good enough or not. But there is an instability that is not because of a material, but because of geometry, and we call that as buckling. So buckling is a geometric instability which doesn't need the loads to go beyond yield stress. The loads might very well be in elastic region, but still you have a failure, that the component that you're designing is no longer fulfilling its intended purpose. That's what failure means, right? When a component stops fulfilling the desired purpose, then it's failed. And so far we have been designing everything based on yield stress or maximum stress or the ultimate tensile strength or something like that, right? But there is a possibility that even in elastic range you have an instability which renders it useless. For example, I have a ruler here, right? What if I apply an axially compressive load on this ruler? Technically, it should show some deformation in the axial direction, right? That's what we have studied. We have studied that if we have a slender beam and if we apply a compressive load on this beam, if it's symmetric, it has cross section which is symmetric, uniform, the material is uniform, then it should just deform in the axial direction. We can decouple axial and bending, right? But what happens in this case? It's a very thin, slender beam. When I apply an axial load, it buckles, right? There is a coupling between axial and transverse loading. So this coupling can be neglected in most cases, especially when you have a tensile load. When you have a tensile load, this is not going to change its position. Any axial tensile load is going to cause just a displacement in the axial direction. But if it's compressive, it changes, right? So this effect or this coupling can be neglected for the beams which are slender but in tensile load, or beams which are of length which is not very high. So buckling is usually seen in slender structures under compressive loads. Of course, if the tensile loads are very high, they also couple with the bending stiffness. That's another effect that can be discussed later, but it's not, at least it's not leading to an instability, right? So especially rotor blades, they have large amount of tensile force or axial force because of the centrifugal force. So they undergo another phenomena where this blade stiffens as it rotates. So that helps researchers to save some weight because the axial load is going to provide some stiffness. But that's not causing any instability, at least. So we will focus our efforts in understanding what buckling is and how can we characterize it for simple systems and possibly for beams. Okay. So quickly some notes about buckling. So far we have been designing components on local stress measures but buckling is a global phenomenon. It can be a local phenomena at times, but the definition of local is different in that case. There would be some component which is small enough to characterize itself as a local region, and then buckling can happen in that region. But buckling is mostly a global phenomena. We do not look at a cross section or we do not look at a local stress measure, which is like a stress concentration or something like that. We are looking at the global behavior of that component. And the study of this critical failure is referred to as theory of elastic stability. So if you look up at theory of elastic stability, you will get all the information unbuckling that you need. So um, when buckling happens, either it it's like a divergent phenomena, which is defined by the potential energy second order derivative going negative, or it can be a slightly stable phenomena, and based on that you might get a post buckling path which is stable. So post buckling path, when I say this, it just means that the system has already undergone buckling. Okay, so for example, in this case, this is stable. If the external conditions don't change, nothing is going to happen to this beam or this cantilever beam. So can I still design my system such that it has a post buckling path which is acceptable? Yes, you can. Let's say if I have a compressive load in this ruler and it becomes like this and it's acceptable to you, then it's fine. You can design or study the post buckling path of a system, and then you can use those characteristics to judge whether you want to characterize this as failure or not. But there might be cases where some slight change in the buckling will lead to a catastrophic failure. So in those situations, as soon as it goes beyond that critical load, we say that failure has occurred. Okay. Okay. So
Is this still an energy method or is this something else?
so this is instability. This is mostly in buckling, a chapter which is, I think, chapter number 14th in the textbook.
Okay.
And we use energy methods in a great detail to understand stability.
Okay.
Yeah. Okay. So in case of buckling, we have to look at two things. One is the geometry of the structure, and the other is the load characteristic. So for example, let's discuss about the loads. Just a small recall. So I'm pretty sure you would have encountered terms like conservative forces, non-conservative forces. You can write potential energy for conservative forces, but you cannot write potential energy for non-conservative forces, right? But what kind of forces do we look at in these cases? For example, if you have a blade, which is a beam-like structure, and there is gravity on the blade at all times, right? Gravity is a dead force. Okay. Let's think about the blade in motion. So it has some aerodynamic loads, right? When it's moving, what is the characteristic of those aerodynamic loads? Lift and drag. So how are lift or drag applied? Let's say lift. How is lift applied on that surface? So lift is always applied perpendicular to the surface, right? So let's say lift will be perpendicular to this axis on the surface. Now what if this blade deforms? What's going to be the sign of that lift, or what are the characteristics of the lift now? It will be perpendicular to the surface again, right? So we see that the forces were applied in vertically upwards direction before, but now it's at some other angle based on the deformation. So this force is following the deformation. We call these forces as follower forces. And they are non-conservative. So the geometry of the structure matters, as we saw in that case of a ruler. If it's a very long slender beam and we have a compressive load, we see buckling. Also, the type of loads that are coming onto the system, they matter. Whether it's conservative, like a dead force, which doesn't change its direction when it's applied. Gravity always is applied vertically downwards, but a follower force or an aerodynamic load is mostly um, non-conservative force and takes the shape of the deformation. Okay, so now we also discussed that there are multiple types or multiple ways in which buckling can happen. One is that you do not have any equilibrium path. When it buckles, the system just collapses. There is another in which the post-buckling path is stable, so that when you keep changing the load, you keep getting a new equilibrium position. There is another type of buckling that is generally seen in structures like these. For example, just push the top surface. So yeah, let me hold it properly. Yeah, oh sorry, yeah. I should have tried this at home before. It's hard to handle, but yeah. Let's try once more. Push it, yeah. So you see that after some time, there is another position which is stable. So if there is a vertical load applied on this object such that you have another path which is stable, that's called snap through buckling. So what this means is that based on the loads in the system, you have another equilibrium path which is far from this equilibrium position, but it's stable. If you keep applying that load again, it's not going to move, right? So this is another type of buckling. So in this course, we'll study all three types. The stable, post-buckling path is stable, post-buckling path is unstable, or snap-through buckling. Okay. Another definition. The load at which the system undergoes instability is called critical buckling load. And the types of buckling that we studied are bifurcation, is referred to as sometimes referred to as classical. It's when the load passes through its critical stage, then the structure passes from its unbuckled state to infinitesimally close buckled equilibrium configuration. So one of them is bifurcation, as I showed, that when the load passes through its critical stage, then the structure passes from its unbuckled equilibrium state to an infinitesimally close buckled equilibrium configuration. Okay. Then we have the second one as finite disturbance. So we define this situation as loss of stiffness is so huge that the buckled equilibrium configuration can only be maintained by returning to an earlier level of loading. For example, we have, let's say, a spherical shell, right, and there is a hydrostatic pressure on this shell, so it will undergo buckling. But if we need a stable equilibrium configuration, it needs to come back to its original position. And then the third one is snap through. So this is characterized by visible or sudden jump from one equilibrium configuration to another equilibrium configuration, for which the displacements are large. So we will take simple systems first. We'll understand them, their post-buckling path, and then we will move on to the complex systems. So when I talk about simple systems, we always begin with 1 degree of freedom system. So let's say I have a rigid bar. Remember, rigid bar, it's not a beam, and it's hinged at this point. It's undergoing a compressive load P. There is a frictionless ring so that the ring can move, and this is attached to a spring. Okay, so let's say that this distance is A from the bottom, the place where the bar is attached, and the length of the bar is L. And when it moves, the angle is theta. So this is a 1 degree of freedom system, right? When it moves, theta is the only degree of freedom in this case, right? So 1 degree of freedom system. And let's study a case 1 where it's a small theta assumption. Okay, so we are assuming that our theta is small. So when we make this assumption, what are the benefits? Theta is almost the same as sine theta and tan theta, right? If you make a small angle assumption, sine theta is close to theta, and same for tangent of theta. Okay, so now what is the energy or the potential energy of the spring? So the potential energy of spring, if this is theta and my length is L, then if I redraw the system, so this becomes L theta, small assumption, small angle assumption, and this was my A, so this becomes A theta, right? So the potential energy for the spring is equal to half K A theta square, when the stiffness constant for the spring is K. So I can write my potential energy of the spring as half K A theta square. And what are the characteristics of the P force? Let's assume that it doesn't move with the deformation. So in a deformed state, let's say this is the undeformed state, then in the deformed state P was applied like this and P is applied like this here. So this is a conservative force, right? I can define a potential energy due to this externally applied conservative load, right? And for potential energy, I need to define the initial and the final states. Okay, so I'm exaggerating the deformation here. It's still a small angle assumption. So this was the initial state and this is the final state that I have, right? This height is L, then this angle is theta, but this length, slant length, is again L. Okay, so we will define the potential energy for this system in the next class and continue to solve this problem for buckling. Okay.